Hi, students. This is a lecture on chapter 27 on wave optics. All right, so we've completed chapters 25 and 26 in geometrical optics. Now, remember, optics is part of electromagnetic theory. All right, and so optics is part, we're still really in electromagnetic theory. Chapter 24, we understand that if we employ the Maxwell equations in source-free space, that we have proven that the electromagnetic field propagates as waves at the speed of light. All right. So recall in chapter 24, when we combine all four Maxwell equations in source-free space, which means no charge distribution, no currents. We find that the electromagnetic field propagates as waves. Traveling at the speed of light. Which we usually call C, all right? So we that was all at the end of chapter 24, or in chapter 24, and that's where I ended what I call electromagnetic theory proper. Then I said we're going to go into optics. So we're in the chapters 25 and 26, and we made an approximation, and a good approximation for many things. And that is, we said, consider a situation where the electromagnetic wave is interacting with objects or holes or apertures, would be the official word for that are much larger than the extent of the wave. If that's the case, the waves, the wave character doesn't really come into play, and the waves act as rays. Okay, so again, in chapters 25 and 26, we made an approximation well, I wouldn't say approximation, we considered a case. Consider a special case where the electromagnetic waves interact with objects and holes, and we'll use the official word for hole in science, it's called an aperture. That are much larger than the wavelength of light. So in this case, light behaves like rays. Light behaves as rays. And this is a very useful case. This is the case in geometrical optics. So this is geometrical optics. Which aptly describes the operation of lenses, mirrors, and the human eye. So the large range of phenomena that can be very well described by geometrical optics, including our own eyes. But if you cannot employ this special case, then you must go to what we refer to as wave optics. Okay, and so wave optics is where you cannot ignore wave characteristics of light. Okay, and that's where we are right now. We have to now employ the wave characteristics of light. We have to consider behaviors such as interference and diffraction. And that's what we cover in this chapter. So in chapter 27, we now consider the general case where geometrical optics does not apply. Where the wave aspects of light come into play. Okay, this describes phenomena such as interference, and diffraction. Not refraction, but diffraction. Okay. So, and we'll talk about all of these in this chapter. All right. So this chapter will be the end of optics, and in fact, it will be the true end of our studies of electromagnetic theory. All right. And so, again, as I've said, optics, I consider that as a separate study to some extent, because really the touch touch and feel of it, I guess it goes much, much different than, say, your electromagnetic theory proper. But indeed, it is still part of electromagnetic theory. With the end of this chapter, electromagnetic theory will be complete. Okay, so with this said, then we have to go back to where we left off in chapter 24 and discuss what light really is. Okay, so light, or let's be more precise here, visible light. Really, optics, our study of optics really deals with visible light. Visible light is an electromagnetic wave. Whose wavelength lambda varies from about 380 nanometers, and that's violet, to about 760 nanometers, and that's red. Okay, that's that. Now, again, as I said in chapter 24, there is a large, the electromagnetic spectrum is very diverse. We are literally looking at a very small sliver of the light that we can perceive with our eyes. All right, so that's what we're looking at. So, like all waves, electromagnetic waves obey speed equals wavelength, or frequency times wavelength. All right, now it turns out that the speed, again, this equation is true for all waves. We started studying waves back in physics 1. We talked about water waves. We talked about waves in a string. The waves on a string. Or we talked about sound waves that would travel. This would be the speed of sound. Waves on a string. The string, that speed would be square root tau over mu. It would be the tension of the string divided by the linear mass density. Well, for electromagnetic waves, we have a different speed, and that is the speed of light. So again, it's just whatever speed is characteristic of your problem. Well, speed of light is the frequency times the wavelength. Okay, this is a universal equation. It just so happens that the speed for electromagnetic waves is that of light. And again, speed of light officially is 299,792,458 meters per second. 186,000 miles per second, if you want. I mean, it is very, very, very fast. So when you talk about the universe, the sun, 93 million miles away at this incredible velocity, this incredible speed, it still takes 8.3 minutes for light to leave the sun to reach us. We represent distances in galaxies and in the universe with what are called light years. Light year is the distance that light travels in a year. So the distance that light going at this incredible speed travels in one entire year, 365 days. Okay, that's called a light year. And the closest star to us after our own sun is Alpha Centauri, or maybe it's called Proxima Centauri, but whatever it is 4.3 light years away. It means light traveling at this incredible speed would take 4.3 years to reach our closest neighbor. So again, that's how big the universe is, but not to digress. But this is an incredible speed. I mean, it'd go across the distance of the Earth in less than a second. Okay, we're talking about or split second. I mean, it is we're talking that so much is covered, and every the light is so fast, and yet the universe is so big. Right now, let's combine a couple of things. Let's combine this equation was something we learned back in chapter 25 and 26. All right, so let's rewrite this equation. We're talking about speed of light in a medium. We're gonna look at it a little bit differently. So we know in a vacuum, C equals lambda F. So let's be very specific about this. This is the speed of light in a vacuum, where there is, nothing to go through. There's no there's no matter to go through. So again, this equation, to be explicit, this is the I call this the general equation for all waves. This is it, but this is light in a vacuum. Okay, vacuum of space, we'll say. What about the speed of light in a medium? Well, let's recall something. Remember back that the speed of light in a medium was given as c divided by n. N is the index of refraction of a medium. Every medium has a different index of refraction. Even air, 1.00293. Remember, we have a different medium. Air, 1.0000293. These are just, I mean, again, we found that the index of refraction actually varies as wavelengths. These are just nominal values. Typically for water, we might use 1.333. Glass, crown glass, typically nominal value 1.52. Diamond, nominal value 2.419, so on and so forth, right? Every medium has its own index of refraction, which does what? It slows the light down. So the light traveling in a medium is slower than in a vacuum by this very simple equation, C divided by N, right? So let's take this top equation of light in a vacuum. Let's divide both sides by N. All right, so let's take this top equation. I have C over N. Again, I'm looking at this equation, F lambda over N. And so we can literally write that, since I know that the speed of light in a vacuum is C over N, I can literally take the left-hand side and write that the speed of light in a medium is F, I'll call it lambda sub N. Okay, lambda sub N is lambda divided by N. Lambda is the speed of light, is the wavelength of light in a vacuum. So the wavelength of light in a medium is shorter than that in a vacuum. Now, one question would be is why doesn't the frequency get affected? Why am I just looking at the wavelength? Well, the reason is you can think of light as a forced oscillation. We go back to our chapter on oscillations. The forced oscillation, no matter what happens, must be the same. So even if my wave happens to change, I still am going to vibrate at the forced oscillation. There's a forced oscillation which will not change. That even if I'm in a different medium, even if I change the parameters, if I, for instance, talk about, well, let's take my simple harmonic oscillator. Well, let's now employ some sort of damping. Let's also employ, let's also put a forcing on it. Well, even if there's damping or not, I'm still going to have the same forced oscillation. So irrespective of n, we're still going to have the same frequency. I'll write this down. So let's take a look at this now. So this tells me here that altogether, that I don't affect the frequency. So in a medium, so the speed of light in a medium with index of refraction n is B is F lambda sub n. Lambda sub n is, of course, lambda in a vacuum divided by n. Okay, and as I said, the frequency of light in a vacuum is the same, and this is very important for people taking the MCAT. This is something that they talk about a lot. They do a lot of this optic studies, and for some reason, the MCAT really likes to talk about this. So let's kind of keep this in mind. So the frequency of light in a vacuum is the same as that in any medium. We can think of the frequency as a forcing frequency. Like we studied in our chapter on oscillations in physics 1. All right, and so it doesn't really matter if I, for instance, have a simple harmonic oscillator, whether I have, no matter what, let's say damping I might have, for instance, like going back to physics 1, I'm still going to have the same forcing frequency. So again, the frequency does not get altered. All right, and so what we see here is that the wavelength does. So let's start off with some problems here. OpenStax 27.1. Again, we're still lined up. We'll be lined up for the rest of the semester as far as OpenStax and Cutnell and Johnson. I mean, the semester is going to take us through chapter 31. We're on chapter 27 right now. All right, in this one. So again, this we will be lined up for the rest of the semester. We will not be out of alignment again. So OpenStax 27.1. All right, what does that say? Show that when light passes from air into water, or sorry, air to water, show that when light passes from air to water, its wavelength decreases to 0.750 times its original value. Okay, so how do we go about doing this problem? Well, this really goes right into what we just got done talking about. And so again, let's remind, I need to get some real estate here. So again, show that when light passes from air to water, its wavelength decreases to 0.750 times its original value. All right, 0.750, remember that number. So here we go. Air into water. All right, so what we're going to do is to say, well, let's remind ourselves here. We have to look up in our optics, our geometrical optics chapter. We have index of refraction of air. We need to look that up. We get that that's 1.000293, about equal to 1. You probably could just work this out as 1, but let's be official about it. And water. So looking at the nominal value for water, you get 1.333. Okay, now lambda air, okay, is lambda in a vacuum divided by n sub air. Okay, again, lambda is lambda in a vacuum. So let's be specific. So again, lambda, wavelength of light in a vacuum. Okay, lambda sub water will be, again, lambda in a vacuum divided by n water. So what's common? Let's do some algebra. Well, let's solve both equations for lambda in a vacuum and eliminate that. Solve both of these for lambda. Lambda, it's going to be lambda air, n air. Equals lambda water, n water. And what are we trying to say? We want to know that lambda water is 0.750 lambda air. That's what we're after. All right. So we're looking for lambda water. Let's solve for lambda sub water. Okay. So doing that, again, n air divided by n water. Multiplied by lambda air. Okay, well, all that's left now is to plug in some values. So n air, so that means that this is equal to, this implies that lambda water is 1.000293 divided by 1.333 lambda air. And if you work that out, you simply get the lambda water is 0.750 lambda air. So the wavelength of light in water reduces to 3/4 of its value of its length as it is in air. It's shortened down to 3/4 of its length. Okay, that's the effect that the index of refraction has. The water The light in water has only 3/4 the wavelength that it does in air. Okay, let's look at OpenStax 27.2. OpenStax 27.2. Find the range of visible wavelengths. In crown glass, n equals 1.52. Index of refraction. Oh, sorry. Got my work mixed up with the problem. So find a range of visible wavelengths in crown glass. That's the problem. All right, that is it. So I started working out looking at my work. So crown glass. All right, so n glass is 1 point. Well, I'll just say n. So n for crown glass is 1.52. You have to look this up. All right. Now, we know that in a vacuum, lambda min for visible light is 380 nanometers. And lambda max is 760 nanometers. Okay, again, 350, this is violet, and this is red. Okay, so we know that in a vacuum, these are the wavelengths of light in a vacuum. This is the range. Light literally will range from 380 nanometers to 760 nanometers. But it does not do so in crown glass. It ranges at different wavelengths in crown glass. Let's see what those wavelengths are. So lambda min in crown glass, well, it's going to be lambda in, and again, I say this is basically, I'm making the assumption here that lambda air is about equal to lambda vacuum. I apologize, I meant to say that. But I'm making an assumption that lambda air is about lambda vacuum about 1.0. Okay, I mean it's 1.000293. If you need to have very precise calculations, then yeah, use the wavelength or the index refraction of air. But in general, you can think of the wavelength of light and air to be about what it is in a vacuum, because index of refraction in a vacuum is very close to that of air. All right, they're very close. So I'm making this assumption right here that literally I'm interchanging the lambda vacuum with lambda air in this numerator, right? In this equation here for crown glass, right? So again, that would be lambda min. That would be the lambda min for the vacuum, 380 nanometers divided by 1.52. We have lambda min for crown glass would be 250 nanometers. Lambda max, again, let me be specific here. Normally, what goes right here is lambda vacuum. Because the index of refraction of air is so close to that of a vacuum, I have just made this approximation. The lambda air is about equal to lambda vacuum. So I'm sticking lambda air right here, interchanging for lambda vacuum. Lambda vacuum is what really belongs here, but I'm making this approximation. Want to point that out. That's the minimum wavelength for in air for visible light. But you have to divide that by 1.52 to index of refraction of your medium, in this case crown glass. The minimum wavelength in crown glass is 250 nanometers. Okay, that's in the ultraviolet. Then lambda max. Well, that's 760 nanometers divided by 1.52. Lambda max will equal 500 nanometers. That's about, I believe, yellow or so, maybe green. Anyway, that's the wavelengths shift. The minimum and maximum wavelengths of light and crown glass shifts. It's not violet to red as we're used to in air, but it's like an ultraviolet value to about probably about yellow or green or so inside a glass. Let's do another problem. Opus X 27.4. So this says analysis of an interference effect. In a clear solid. Shows that the wavelength of light in the solid is 329 nanometers. Knowing this comes from a helium neon laser, and has a wavelength of 633 nanometers. We know the wavelength of the helium neon laser very, very well. Has a characteristic red color, reddish orange color. In air, is the substance zircon or diamond? Again, we're trying to see if we can find a fake diamond again. Is a substance zircon or diamond? And this is another test one can do if someone passes them off of what they call a diamond ring, and it's not really diamond. It may look like it to the unaided eye, but here's a test that you can use to show that someone's passing a fake. So analysis of an interference effect in a clear solid shows that the wavelength of light in the solid is 329 nanometers. Knowing that this comes from a helium neon laser and has a wavelength of 633 nanometers, something we know very, very well. We'll explain that when we get to quantum mechanics. In air, is the substance zircon or diamond? Okay, so I need a little bit of real estate here. Very similar to the last problem. I did it because I think it's really interesting. All right, so again, lambda sub n, whatever n is, we don't even know. It's mystery material here. Okay, but we do know this. We do know that a very well-known wavelength of light, we know that helium neon laser, we know very, very well what its wavelength is. So in air, we know that the helium neon laser, that laser you always see in the physics lab, it always is a red-orange kind of a light. That's helium. That's specifically a helium neon laser. We'll talk about when we get to chapter 30. I'll explain all about how the helium neon laser works. But for right now, let's just take this as a given that we understand. We know the wavelength of light of helium neon laser very, very well. 633 nanometers. Now we pass that light into this unknown substance. We find out that the unknown substance. We do an analysis and we find out that the wavelength of light, and this is also something that's very easy to do. You can do this in the sophomore level physics lab. Figure out what the wavelength of the light is, and you find out that it's 329 nanometers. So that's interesting. Well, let's again make the assumption, make the approximation that lambda air is approximated as lambda vacuum. And then we can use our equation. Well, lambda sub n, whatever it is lambda air. And again, I remind you, and again, that's divided by n. I remind you that lambda vacuum really belongs here. But given that the index of refraction of air is so close to that of a vacuum, I'm making this approximation sticking lambda air in here. And generally speaking, given that there is such a closeness, unless you're doing highly precise calculations, which you have to go one step of algebra more to also figure out, kind of like what we did in the very first problem we worked on. We actually utilize lambda air, but here I'm making an approximation to do, a little bit less work. All right, so again, that's generally how you might operate. If you only know things within 3 decimal places, you're just doing extra work for nothing. You're doing 50% of the effort to get an extra 1%, right? You're essentially this is good enough. So in that particular case, we can solve for n. So again, we switch partners here. N is lambda air over lambda sub n. We know what this is. Lambda air is 633 nanometers, can only have 3 decimal places of precision anyway, divided by 329 nanometers. I come out to find that n is about 1.92. So we look in the table of indices of refraction, and zircon is about 1.923. Diamonds is about 2.419. So if someone's passing you a ring and telling you that, or passing you some stone or mineral and tells you that this is diamond, then they've lied to you. Because you do the physics and you find out that really this has the same index of refraction as zircon. This is what they call cubic zirconium. All right. So again, 1.92 is after the laboratory test. So this is indeed very likely zircon. Okay. Okay, so first section, we realize here that the index of refraction is a function of wavelength. Now, let's go back. Now, again, when we got to chapter 24, we literally was about to touch the 20th century. So we were right around 1870 with the full-blown electromagnetic theory by Maxwell. Then we kind of took a step. We took many centuries step back as we went to optics. We talked about the law of reflection and the law of refraction. Well, those have been known about for a while. I don't recall when Snell's law came into being understood, but it certainly well preceded Maxwell. And Hero's law, well, we're talking about Hero of Alexandria. We're talking about ancient Greece when we understood the law of reflection. So that goes back a ways. So with our study of light, that really goes back to Isaac Newton. And so Isaac Newton was a firm believer in a corpuscular theory of light. I.e., light consists of a stream of particles. All right. So in physics 1, we learned that Isaac Newton wrote one of the greatest scientific treatments or treatises in the history of humankind, maybe the greatest. And that was the Principia. So in physics 1, we learned that Newton wrote the Principia. Which is considered the greatest scientific work known to humankind by many people. In the Principia, are the 3 laws of motion. And the law of universal gravitation and the law of universal gravitation. So he brought out 4 of the laws of mechanics. One of the fundamental force laws and 3 of the laws of mechanics. So we're back to talking about Newton. So again, Isaac Newton, the firm believer in a corpuscular theory of light, i.e., light consists of a stream of particles. In physics 1, we learned that Newton wrote the Principia, which is considered the greatest scientific work known to humankind. In the Principia are the 3 laws of motion and the law of universal gravitation. We also know that Newton developed calculus. He called it the method of fluxions. So Newton also developed calculus which he called method of fluxion. He had the famous calculus wars with the German polyglot Gottfried Leibniz. So Newton had the famous calculus wars with the German polyglot Gottfried Leibniz. Who co-developed calculus, basically, who independently developed calculus. In fact, we use Leibniz notation for most things more than Newton's. Leibniz notation is much more natural. And Newton was a very feisty person. And he did not, and Leibniz is one of those people he hated. So Newton was fly off the handle. He was very prone to anger. And if you challenged him, he would go into a rage. And so Leibniz is one of those people he absolutely hated. I'm not sure if Leibniz really understood why Newton hated him so much, but anyway, the important thing in our studies here is that Newton wrote the book on optics. So Newton also performed fundamental studies of optics. And he wrote the book, if you will, on optics for a while. You can buy this book in Barnes and Noble or Amazon. He wrote. I own a copy of it. He wrote the book on optics. And it was called Optics with a K. I don't know if the English spell optics this way today or not, but a lot of times in the old English, a lot of words that we might end with a C, like magic, for instance, it would be spelled with a K. And magic would be M-A-G-I-C-K. Optics, O-P-T-I-C-K. So again, his book on optics was what he literally wrote the book on optics. So people got to believe that Newton had the final answer. You should not challenge him. He is. I mean, who would challenge the guy who who developed the laws? I mean, who wrote the Principia? And and so most people studying optics adhere to Newton's philosophy. They're called the Newtonians. Okay, so there was no wave theory of light at that point in time. It was all dominated by Newton. Okay, and so Newton's view that light was a stream of particles prevailed for over a century after his death. And like we humans like to do so much, we divide ourselves, right? So scientists, great scientists, in fact, scientists who were adherents to Newton's corpuscular or particle theory, were called the Newtonians. All right, and so, you know, it would seem almost insane to argue the truth that Newton put out, given that Newton was so successful. He had this incredible stature. So who would challenge him, right? But scientists need to remember, though, that your name, you know, essentially anybody can be wrong no matter what your name is. So we kind of get into this whole point is we're going to look at first what's a minority view on light, which is the wave theory, and eventually it prevailed. But again, it was an uphill battle because people were enamored with Newton, right? So in science, just a general scientific philosophy. We're leaving physics for a moment. In science, you are right because you're right. It sounds very simple, but people lose track of this sometimes. Okay, and in science, it does not matter what your name is. You can still be wrong. And we will talk about in our next chapter, chapter 28, we're going to talk about the special theory of relativity. The special theory of relativity, we see that Albert Einstein showed us that Isaac Newton was wrong. His mechanics was wrong for physics at high speeds. Now, everything we've talked about with Newton so far is totally fine. But when you talk about particles approaching the speed of light or getting a good fraction speed of light, Newton's mechanics break down. They are wrong. They need to be fixed. That's what chapter 28 is all about. It's called the special theory of relativity. Einstein himself was very, very wrong in the later part of his life. So Einstein had great successes. You know, certainly the greatest physicist who ever lived. Einstein, you know, was laid down the seeds of quantum theory. We'll talk about that when we talk about chapter 29. Einstein is responsible for the special theory of relativity, which is chapter 28. Einstein was the first to theoretically explain atoms. Einstein, we'll talk about that in 29 and 30 as well. Einstein brought forth the correct understanding of gravitation. That's a general theory of relativity. And that's what made Einstein a rock star. Einstein laid down the fundamentals of a laser. We have lasers today because of the theoretical work done by Einstein. Einstein wrote the letter to President Franklin Roosevelt that got the Manhattan Project in place. Einstein, as a single human being, is responsible for putting the entire human race into the nuclear age. But as great as Einstein was, he was very wrong in the latter part of his life. In fact, his productive years in his life probably ended right around his late 30s. The rest of his life, he didn't want to accept quantum mechanics. He had kind of I would say, a philosophical / religious problem with quantum mechanics. And he wanted to develop a unified field theory that did not involve quantum mechanics. And he basically wasted more or less the rest of his life trying to accomplish that. And in fact, people were waiting with bated breath on Einstein's next great work, because Einstein was so successful in all the things he did previously. When he finally published a paper on his unified field theory, it was an embarrassment. People were all like, they're excited. They took the pages of the paper and they pasted it on their windows, and they were all excited about this new development by Einstein. Then the physics community began to read the paper, and it was basically nonsense. So as great as Einstein was, even he could be wrong. So the idea is, in science, it does not matter what your name is, you can be wrong, even if your name is Newton or Einstein. All right. And again, in science, unlike other human endeavors, you are not right because you wear a special robe or a special hat. You're right because you're right. Okay, and that's what I always tell people. In science, unlike other human endeavors, like law or religion, for instance, you are not right because you wear a special robe or a special hat. Okay, that does not make you right. Now, enter the picture of the first wave adherent. His name is Christian Huygens. Now, Christian Huygens was a contemporary of Newton. Again, the wave adherents, you can really count them on one hand. Okay, so the first person, the first wave adherent, or wave theory adherent, or the first adherent, I would say, to a wave theory of light was the Dutch physicist, brilliant, they call him the Dutch savant, the Dutch physicist Christian Huygens, one of my favorites. All right, first adherent, I would say, of a wave theory, at least a major adherent of a wave theory of light, was the Dutch physicist Christian Huygens. Again, that's pronounced Huygens, Huygens. Huygens is usually how I hear it pronounced. Okay, he put forth Huygens advanced his wave theory of light in 1678. Okay, Isaac Newton was born in 1642. So Isaac Newton was about 36 at the time. So again, you know, Isaac Newton was active at the same time Huygens was active. Now, Huygens' theory is much more primitive. And that put forth then the true electromagnetic theory put forth by Maxwell in 1870. But it is useful still to this day. I mean, Huygens in of himself was a first-rate genius as well. A lot of people don't hear about him, but he is great astronomer, excellent physicist. His name he is oftentimes called the Dutch savant. All right, and so he's somebody who lived at the same time as Newton, and he was brilliant like Newton was. Not as accomplished, of course, but how many people actually are as accomplished as Newton? All right. Now, what is Huygens' theory? And I mentioned Huygens' theory a little bit in the beginning in the chapters 25, 26, but just briefly, I call them Huygens wavelets. Okay, Huygens wave theory. Is based on a geometrical construction. Okay, that allows us to tell where a given wavefront will be set up at any time in the future. Right? Huygens wave theory is based on a geometrical construction. It allows us to tell where any given wavefront will be set up at any time in the future. If we know its present position, let me add that on. If we know its present position. And I'll start out with some simple pictures. Okay. Now, so again, Huygens wave theory is based on a geometrical construction that allows us to tell where any given wavefront will be set up at any time in the future if we know its present position. All right. Now, I'm going to now write down what Huygens principle. It's based upon Huygens principle. So where are we set up the wavefront? Again, this will become more clear when I show you a few pictures. So this construction is based on Huygens principle. Which is officially all points on a wavefront and that's the front of the wave coming at you, serve as point sources or of spherical secondary wavelets. After a time t, the new position of the wavefront will be the surface of tangency of the secondary wavelets. All right, we're going to use this principle to show you how we can derive the Snell's law. All right, so the construction is based, again, the construction that we're talking about is based on Huygens principle, which is all points on a wavefront serve as point sources of spherical secondary wavelets. After time t, the new position of the wavefront will be the surface of tangency of these secondary wavelets. So what all does that possibly mean? So let me show you a picture. We'll start off really simple. So talk about Huygens principle. So let me show you a picture here. I did some PowerPoint constructions here, so let's hopefully they look good to you. All right, let me share my screen. And I'm going to show you just a plane wave. Real simple. And what we see here is, we see that at some point initially, we have a wavefront AB. Okay, so we have a wave that's coming. It's a plane wave. That means if you're imagining yourself on the beach, for instance, you see a wave coming at you. You can kind of almost draw a line, across the base of the wave. Well, that's your plane wave. Your plane wave is coming at you. Okay, this is a light wave in this case. And what it says is that, well, the wavefront of the wave is you can draw a line AB along the wavefront of the wave. Now, each point on that wave, and I drew some points out, each point on that wave can serve as secondary spherical wavelets. It means I can imagine, I know the wave is propagating at the speed of light, c. I can imagine that at a given amount of time, each of these waves will be like a spherical bubble. Each of these points will be like a spherical bubble. And they'll be expanding at the speed c. And they'll have expanded a distance d equals ct. So they'll have expanded in radius by an amount d equals ct in a time t. Again, the waves are expanding at their speed. Okay, so these spherical wavelets are expanding. And a time t later, the wavefront, we understand, will have moved, it should have moved the distance ct. It's going to speed of light, right? Well, if we took a look at the Huygens theory, he is saying that all of these secondary, all these points along the wavefront serve as secondary wavelets. Each one of them is going to be like, imagine a bubble being blown. And the bubble will be a radius ct. And then you draw a line of tangency to the new set of circles. Tangency meaning that I'm drawing a line that is tangent to all of these circles. And you find out that the line of tangency is yet another wavefront. We call it DE. And I can do this all over again. I now have a new wavefront, and I can consider all of these points along DE as secondary spherical wavelets, and each one of those will be blown a bubble. that if I allow another time t to go by, it'll again have blown out bubbles of radius ct, and I can draw another surface of tangency, and I can draw another wavefront. And I can explain through Huygens wavelets why we have these plane wavefronts. Essentially, I have a plane wave. So let me stop sharing my screen here and kind of show what we're talking about, just briefly. All right, so what I have here is initially a wavefront. Okay, here's a wavefront. Here's a wave that's traveling along, let's say in this direction. I have a wavefront. I called it AB. And I said, well, this is a wavefront. The wavefront is traveling. Okay, this is a front of a wave. This is a wavefront. It is traveling along in this direction. Now, Huygens says to consider all the points on this wave. I'm just picking out certain ones, but really it's an infinite number. Each of these points on the wave is thought of as the point source of a secondary spherical wavelet. That means I can imagine the spherical wave, kind of like you drop a rock in a pond, right? You drop a rock in a pond right here. What happens? You see spherical waves forming, right? You see little wavelets forming from a rock dropped in a pond. These are spherical wavelets. I drop a rock in the pond, and I have little ripples, little spherical ripples. Well, Huygens probably saw this in a pond over, where he lived, and got this idea, right? But imagining here that this wave, which we understand waves as a disturbance. Let's say at a time, I allow a time ct to go by, and each one of these spherical waves has, doing the best I can, my art skills aren't so great, but I allow each one of these. Each one of these waves is expanding out by a distance d equals ct, right? Again, the distance, the wave spanning out is the speed of light, the velocity times the time. I'm allowing a time. So this is a time t later. I'm allowing a time t to go by. And what Huygens says is that you draw a surface of tangency to these circles. Doesn't look too good here, but draw a surface of tangency, you get the next wavefront. He called that dE. Again, this is a line or surface of tangency. I'll call it a line of tangency. To spherical wavelets. That are centered about points on a wavefront DE, or sorry, AB, at a time for a wavefront DE at a time t later. All right. So again, this is showing you. This is basically showing, or we are understanding. This answers the question of how plane waves propagate. Why do they propagate as plane waves in space? Well, if we look at Huygens' theory, Huygens says that all the points along the wavefront are the sources of secondary spherical wavelets, and that the new wavefront is a surface of tangency, or again called the line of tangency, to these spherical wavelets. And tangency means tangent, as you can imagine. Okay, well, you might say, okay, well, that's interesting, but can you use this to describe something else? Yes, let's now use Huygens theory to understand the law of refraction. All right, so let's understand that now. So I'm going to show you a picture. Now I want to make a statement here really quickly that I'm going to show you a set of pictures from a textbook, one of my favorite textbooks of all time. It's Fundamentals of Physics by Holiday and Resnick. Again, I just want to, give credit for where credit is due for the various pictures, but the set of pictures that I will show, in this lecture is from Fundamentals of Physics by Holiday and Resnick. 1988. Okay, so again, I like a lot of the pictures. I'm going to show pictures not only in this chapter, but also in the relativity chapter as well. I also think that they did a great job there as well. So again, a lot of pictures I'm going to show here. I'm going to rely on them. Again, Fundamentals of Physics by Holiday and Resnick. I'm just giving credits for the pictures I'm going to show you. Okay, so again, these are officially where those pictures came from, and so I want to give the appropriate credit. Okay. So let me show you a very nice picture. And maybe I wrote it out here. Give me a moment. I may not have opened it. Ah, here it is. Okay, sorry about that. Okay, it's a very picture-oriented lecture. So let me just double check I did the right thing here. Yeah, it's like this picture. There it is. Okay, so let's take a look at a picture here. Now, I'm going to kind of try to blow up the picture a little bit, but we notice that we have a wave that we have air on the top and glass on the bottom. We're seeing more and more glass. We're looking at a wave front that is going into glass. Now, probably the best picture you can look at is picture B. But let's consider, first of all, picture A. And let me kind of look at these a little at a time. And let me try to focus a little bit, if I can. Let me see here. there's a way of zooming this better. Oh, here we go. Resize it. This may not work, so. You know what? It's not gonna work. Okay. We're gonna have to just I'm gonna have to point things out at you here, I guess. All right, so you have part A of this wave. Now let's make it a point to understand here that this wave is has a wavelength lambda 1. So again, the wavelength in air is lambda 1. Now lambda 1. Now this wave is actually making an angle with the surface of theta 1. Now it turns out that that theta 1 is the same as the angle of incidence. Now as the wave comes into the glass, we notice that the surface of tangency along here, that some of this wave is being slowed down because it's going through the glass. The wavefront is slowing down, and it's only going at a distance lambda 2 in the glass, still at lambda 1 outside the glass. Now in the glass, it makes an angle theta. It has a distance lambda 2. It's making an angle of theta 2. The surface is with the secondary wavefront. So let me try to redraw this a little bit, that we can kind of see it. All right. So again, it's a little bit hard to see. What we're seeing here is that. I'll put that picture back up in a moment. We have a glass-air interface. Now, outside, we'll notice that we have a wave that's going to bend. All right, and so essentially, outside, the wavelengths are coming in they are at a wavelength lambda 1. They're traveling lambda 1 in time. Trying to draw this nicely. Try to blow this up here. Here's our air-water interface, or air-glass interface. Up here is air, down here is glass. All right. Now, imagining like in this point here, we have wavelengths of light that are going to have a distance lambda 1. Now, these wavelengths as they come in are going to have a reduced distance. Let me take a look at my pictures, since my drawing skills are not so great. So as these waves come in, the same distance, if I consider, out here, the same distance is going to be reduced. And so what's going to end up happening is the wavelengths inside the glass are only going to be going at lambda 2. And so I know that, for instance, we know that the velocity, the waves are going to have a velocity, say velocity 2 inside the glass and a velocity 1 in the air. All right. So I can essentially say that I know that the velocity 2 is going to be less than velocity 1, first and foremost. I do know that much. All right. Now, one of the things I want to look at here is to say, well, okay, so if that's the case, I know that, for instance, that the wavelength of light, the wavefront is making angle theta 1 with respect to the plane of the air glass plane. Now, one of the things I claim is that is the angle that is actually the same as the angle of incidence. So is that true? Well, let's take a look here. If this is the case, then we can imagine drawing a little triangle here. Okay. And the angle, if I imagine this being an angle of incidence right here, let's just imagine that I draw a vertical downward. Well, what do I know? I know that this angle right here has got to be 90 degrees minus theta 1. All right. All the angles of a triangle is a right triangle. Again, it's a wavefront coming in. I'm drawing a line from the wavefront. And this is the direction in which the wave is traveling. The wave is traveling, a velocity vector for this wave would be going like this along this line. This would be a right triangle. This is 90 degrees minus theta 1, which means that this is also theta 1. This is the angle of incidence. So theta 1, which happens to be the angle that the wavefront makes with the air glass interface, is also the angle of incidence of that we talked about in chapters 25 and 26. Now on the other side, we have an angle theta 2. And we can think about with theta 2, we can also, again, this is not as big of a triangle here, but we can also do the same kind of argument. We know again that the light is going to be going this direction. All right, and so we can also make a statement here that okay, that's got to be theta minus angle theta. This has to be 90 minus theta 2, and over here, this would also have to be theta 2. All right, so again, this would be the angle of transmission. All right, and so let me redraw this a little bit even bigger. I apologize. I like to actually try to draw these triangles out so things make sense. So here we go again. Let me try to draw this as big as I possibly can. And we have air up here and glass. Again, you don't have an artist for professor here. So, all right, so we have wavefronts coming in. These have lambda 1. And why is that? Well, the waves are traveling, they're basically traveling, they're traveling in a certain, so in a time t, we have that lambda 1 is v1 times t. Again, we're considering everything being done at a particular snapshot of time t, a certain time duration t. All right, so these waves travel at a velocity v1 and at lambda 1. Now these same waves are going to travel at a slower velocity inside the glass medium. These will be lambda 2, these wavelengths. And we would say, well, lambda 2, of course, is v2 in that same amount of time t. And that v2, which is the speed of light in glass, has got to be less than v1. Now, as I showed you a moment ago, if this is angle theta sub 1, then we happen to know that if I imagine light is going along this plane here, that this is going to be, so let me kind of draw this out. Draw it. I think I'm do a better job drawing it over here. We'll say this is theta 1, and we can draw a line right here, and we can understand that this is also theta 1, because this is 90 degrees minus, this is 90 degree minus theta 1 right here. This complete this triangle. This is a right triangle. Okay. On the other side, we have a triangle we can draw out with respect to theta 2. And we understand here that the angle that this wave inside of the glass makes is theta 2. And oh, by the way, this angle would be 90 minus theta 2. And if I were to draw a normal, that the angle with the normal would be theta 2 as well. So this angle right here would also be theta 2. So again, theta 1 ends up being the angle of incidence that we talked about in chapters 25 and 26. And theta 2 ends up being the angle of transmission. Again, let me show my, 1 second, make sure I'm not off the board. Okay. Yes, angle of transmission. Even though they are the angles really defined with respect to the interface. All right. Now, let me take a look at something really briefly. I'm gonna take this picture and blow it up. Okay, so I'm gonna take this little picture right here, and I want to blow it up out here. Okay, so I have a piece of the interface. On one side of the interface, I have the wave in air. Again, this is the air side. And I have an angle theta 1. And I have it, where it basically connects with the next wave. Now, on the bottom, what do I have? Well, this wave, this angle bends in. This angle becomes theta 2. And again, I have another right triangle. This is a right triangle, and that's a right triangle. Now, in the language used by in Holiday and Resnick, the language used by Holiday and Resnick, let me share my screen briefly here. He calls this triangle, he says that he refers to this letter right here as C. He refers to, or they refer to the letter over here, they call it H. And they have they refer to the wave as having moved from E to C in air, and they refer to the wave as moving from H to E prime in the glass. So essentially, the picture in the book, the picture states that the wavefront in air moves a distance lambda 1 from E, actually it's I don't know why they use these terms, but E to C in the same time T that the wavefronts in glass moves lambda 2 from H to E prime. And those are the letters that they use. All right. And so what they're pointing out is that there's a certain amount of time that's transpiring. There's a certain amount of time that's transpiring. That in air, the wavefront moves the distance lambda 1 going from E to C. In the same time, again, this is a line of tangency. This is the same wavefront. It's bent now. It doesn't move as fast in the glass. So it is bent because it doesn't move as fast inside the glass. And so the same amount of time t, the wavefront in glass moves the distance lambda 2 going from H to E prime. So in my blown up picture here, this is C, this is our E, this is our E prime, and this is our H. All right. Now, we're going to do a little bit of trigonometry. So again, the point is wavefronts in wavefronts in air move faster. They cover a larger wavelength. They cover a larger lambda 1 in a given time t. In that same amount of time t, wavefronts in the glass move slower. They move at a slower speed v2, and they cover less ground lambda 2. And so we bring out this picture. Again, the wavefront goes from E to C in air in the same amount of time that it goes from H to E prime in glass. Okay, this is a lambda 1. This is lambda 2. Okay, so let's do a little bit of math here now. And so this distance here, this is really lambda 1. That distance along that way, this distance in the glass, this is really lambda 2. All right. So what we're seeing here, I'll try to keep my beautiful picture up here. What we're seeing is that in a given time, that we know that in a given time, t, solving these equations up here, I can write that that's equal to lambda 1 over v1. That's also equal to lambda 2 over v2. Again, just making very simple calculation. I know that the wavefront in air goes the distance lambda 1 in a time t, going at a speed v1, and the wavefront in glass goes the distance lambda 2 at a speed v2. Again, the times are the same. I'm considering the same time duration. Let me rearrange this equation a little bit, and I can write that lambda 1 over lambda 2 is then equal to v1 over v2. Okay, again, and this is purely a geometric argument, understanding that the waves move slower in glass than in air. Now, let us use geometry now to re-express lambda 1 and lambda 2. So I like to look at some basic trigonometry. Now, this is my hypotenuse, HC. In fact, it's the hypotenuse of both triangles, the upper triangle and the lower triangle. If I look at the upper triangle, I can imagine here the upper triangle. Let me, we understand this. So I'm gonna start putting stuff in the parking lot here because I have a little real estate problem. So air and glass. All right. So what do we know right now? We know that lambda 1 over lambda 2 is v1 over v2. Now we're gonna do some trigonometry. We say, okay, great. Let's re-express lambda 1. How do we do that? Well, it turns out that HC is the hypotenuse for the right triangle in air and in glass. So I can do some basic trigonometry. Okay, let's see here. I can say that that the, let's see, this is the angle. So let's see, I have a opposite is my lambda 1 divided by a hypotenuse. Well, okay, fine. I can say the sine of theta 1 is what? The opposite, lambda 1 divided by the hypotenuse HC. And I can do the same thing for lambda 2. Opposite is lambda, sorry, so opposite for theta 2 is lambda 2. And again, my hypotenuse is the same. So I can say the sine of theta 2 is lambda 2 by the same length, HC. So what I can do is eliminate HC. Let's solve HC for both. So HC, or I can write, well, let me just divide one equation by the other. So let me say the sine of theta 1 over the sine of theta 2. I'm going to divide one equation by the other. I can always do that. No one says I can't. So let's see, sine of theta 1, that's lambda 1 over HC. Divided by lambda 2 over HC. HC cancels out. So this tells me that the sine of theta 1 over the sine of theta 2 is lambda 1 over lambda 2. So I have another relationship. I have a relationship now with the index of the angle of incidence, angle of reflection, or angle refraction. So great. I have another equation. Again, what did I do? Again, I'm looking at this triangle. I know that this is the air part of the triangle, and the lower triangle is the glass part. All right. In air, the wavefront goes a distance lambda 1 in a given time t. In the same time t in glass, it goes a distance lambda 2. And in this construction, I have two right triangles that share the same hypotenuse, which I have labeled as HC. Okay, so I know this equation already from the fact that I used the very basic equation of the displacement of the wavefront from physics, from chapter 2 of our physics. And now I'm using trigonometry, and I'm saying, well, okay, well, sine of theta 1. Okay, what do I know about this? Well, I know lambda 1. I know that's of course of interest, and of course they share the same hypotenuse. Well, that should be of interest too. So sine of theta 1 is the opposite of our hypotenuse. Lambda 1 over HC. Sine of theta 2, opposite, lambda 2 over the hypotenuse. Again, lambda 2 over HC. So I now can combine these equations, and I get sine of theta 1 over sine of theta 2 is lambda 1 over lambda 2. Great. That's another equation of my parking lot. Again, pure geometry. Calculus didn't exist back then. So what Huygens was doing is a purely geometrical construction with some basic physics ideas from Galileo. All right, so what did we just say? We just said that the sine of theta 1 over the sine of theta 2 is lambda 1 over lambda 2. All right. Lambda 1 over lambda 2. So there you go. Now, at this point, we can combine these two equations. We can eliminate lambda 1 over lambda 2. So at this point, we can then say we can eliminate the quotient lambda 1 over lambda 2 and write that the sine of theta 1 over the sine of theta 2 is v1 over v2. All right, we're almost home free here. All right, so now what else do we know? So we now know that sine of theta 1 over sine of theta 2 is v1 over v2. Let's put that in the parking lot. Again, I apologize for my limited whiteboard here, but we've already used these equations to our heart's content. And what we have left over now is this. Sine of theta 1 over the sine of theta 2 is v1 over v2. All right, now we're going to use the concept of the index of refraction. We know in general that the speed of a wave is the speed of light in a vacuum divided by the index of refraction. So what I can say is the sine of theta 1 over the sine of theta 2 is, okay, what's V1? Well, it's going to be the speed of light in a vacuum divided by the index of refraction of medium 1, N1. What about V2? Well, again, that's the speed of light in the vacuum, same speed of light, over the index of refraction, N2. Okay? And that tells us then that I can now write that the sine of theta 1 over the sine of theta 2 is N2 over N1. All right? And what else can I do at this point? Well, I can just cross multiply, and I have Snell's law. So I cross multiply, I get Snell's law, the law of refraction. N1, sine of theta 1 equals N2. Sine of theta 2. Now, that is deriving the law of refraction from Huygens wavelets. Now, if you're taking university physics, I would ask you to do the following question. I'd ask you to derive the law of reflection for me, also using Huygens wavelets. That would be a problem left to the student. And again, I did the harder problem. You know, the law of refraction is a harder problem with Huygens wavelets. Law of reflection would be easier. But anyway, you look at it, what Huygens, basic theory tells you is that I can get the law of refraction and the law of reflection from other means. Hence, there are not fundamental laws of physics. So again, Huygens wave theory is the first theory. He's the first wave adherent, or a wave theory adherent, or the first adherent to the wave theory of light. Again, Newton dominated light, or the theory of light with his optics, his corpuscular theory, and we humans, again, we like to divide ourselves, and so many physicists put themselves on the Newton's winning team, if you will. Newton with his stature, they align themselves with Newton. But in reality is, science isn't done that way. Science is done via experiment. Science is done via logic. Science is not done because you happen to like a certain person more than somebody else, or you happen to think that this person's got great stature. That's not the way science is done. Okay, so now Huygens theory, as true as it may be, did not get, again, it was not convincing to people, or enough people. Clearly, it shows you there's some sort of a wave property, but again, Huygens wave theory, even though it can be used to derive the law of refraction, or law of reflection, and the law of refraction. It was not sufficient enough to convert the Newtonians. All right, so again, they still, and so again, you cannot, the problem though is Newton's corpuscular theory still cannot explain interference of light or diffraction. Which we will find out is the flaring out. So light flares out of light when it passes through small apertures. Aperture is a fancy word for hole. All right, so Huygens wave theory, even though it can be used to derive the law of reflection and the law of refraction, it was not sufficient enough to convert the Newtonians. We saw it a war raging. Newton's corpuscular theory still cannot explain interference of light or diffraction, which is the flaring out of light. Okay, so give you an example of Huygens diffraction. So let me show you a picture again from Holiday and Resnick. Let me share my screen. Nope, that's not it. Give me a moment here. There it is. Okay. I have a lot of pictures I'm going to show you today, so I'm trying to keep one picture. When you look at the thumbnails, it's harder to see one from the other here. I'm not seeing it here though. Oh, here it is. Okay. So what you're seeing here is an example of diffraction. So again, this is from a page of a book here. So you see light that's passing by. It's in each case, it passes through a slit of width A. You can think of this as a hole of diameter A, if you wish. But light is passing through this slit. We're looking at it as a slit in 2 dimensions. Now, all right, the light happens to have a wavelength lambda. Now the slit is 6.0 lambda. So the slit width is actually about 6 times the wavelength of light, yet you still see this flaring out of light. Light flares out. It doesn't pass through as a plain light any longer. It on the other side of this first picture, it flares out. If you look at the second picture, the middle picture, again, looking at the same hole, it's a width A, but we're gonna cinch make the hole actually looking at the same wavelength of light. Now we're gonna make the hole smaller. So again, in part A, the A was equal to 6.0 lambda. Now we're gonna make A smaller. And notice that now it's 3.0 lambda, 3.0 times the wavelength of light, and it flares out even more. In the rightmost picture, we make A even smaller, 1.5 lambda, it flares out even more. This process of flaring out, the flaring out of light, as it passes through a slit or a hole or an aperture, is called diffraction. In fact, the smaller you make your hole, the greater the flaring out of light. Again, you can see this with these pictures. The leftmost hole, the width of the slit was 6.0 lambda. That's 6.0 times the wavelength of the light that's coming through it. And we see that the light flares out slightly. We make the slit even skinnier. We make it 3.0 times lambda. And the light flares out even more. We make it even skinnier, 1.5 times lambda, and it flares out even more. The skinnier, the smaller you make your aperture compared to the wavelength of light, the more the light flares out. This process is called Huygens diffraction. This is called diffraction. All right. So what I just showed you in pictures is what is called diffraction, the flaring out of light. So the flaring out of light as it passes through on small apertures is called diffraction. Newton's theory could not explain that. So again, that's an argument that you need a wave theory. All right, and so let me, as I show these pictures, I'm going to kind of bring some of them down so I can make less confusion here. All right, that one's done. All right. Okay, so now we had our first wave adherent, and that was 1678 Christian Huygens. The world had to wait until 1801 for its next major wave adherent, and that was a physician and physicist by the name of Thomas Young. All right, and so again, going back to the history, we had to go all the way back to 1678. So although Christian Huygens thought the light was a wave, Sir Isaac Newton did not. Okay, so basically Newton felt that the explanation there are other explanations for color and interference and diffraction. So Newton felt that there were other explanations. He didn't know the answer, but he didn't think it was waves. For color, interference, and diffraction. I mean, he saw these effects himself. It's not like Newton was ignorant of these effects. He himself did an experiment where he had a prism in his office, and he used a prism to actually show dispersion in colors. Newton saw these effects himself, but did not adhere to them being a result of a light being a wave. He felt that there's another explanation. Again, as I said, owing to Newton's tremendous stature, his view generally prevailed. And again, scientists should know better. But we're human first. Okay. Now, again, that was the first wave adherent. You can count them on one hand. You had to wait until 1801 for the next one to come along. Okay, as I just said. So, so the acceptance of a wave theory of light had to wait many years. In 1801, the English physicist and physician, Thomas Young. So he's a doctor. Thomas Young has his name on a few things in physics. I mean, but it's probably the most famous one is his famous what's called a double slit experiment. So again, he lived from 1773 to 1829, and he performed his famous double slit experiment. So you type in Google double slit experiment, you will get Thomas Young. It's a famous experiment, one of the most famous ones in physics. And we're going to talk about it now. So again, the acceptance of a wave theory of light had to wait many years, much because of Newton's stature. In 1801, the English physicist and physician Thomas Young, so between 1773 and 1829, performed his famous double slit experiment. All right, we're gonna discuss the double slit experiment next. But Thomas Young showed that light in this experiment. He showed that light indeed performed interference, and he was able to predict it. In fact, he was able to use it to actually give you the first measurement of the wavelength of light. So again, you had a really hard time ignoring him, right? So in the 1801 Young experiment, Young established the wave theory of light on a firm experimental basis. Okay, and he basically by showing that two overlapping light waves can interfere with each other. Can't explain that with Newton's corpuscular theory. All right. So, and again, we're going to talk about this experiment quantitatively in a moment. In the 1801 Young experiment, Young established a wave theory of light on a firm experimental basis by showing that two overlapping light waves can interfere with each other. Okay. Young's experiment was especially convincing because he was able to deduce the wavelength of light. From his experiments. Which are the first measurements of this quantity. So we're talking about not only is light a wave, I can actually measure the wavelength of it. Well, that you're probably onto something. All right. So again, in 1801, a Young experiment established the wave theory of light in the firm experimental basis by showing that two overlapping light waves can interfere with each other. Also, Young's experiment was especially convincing because he was able to deduce the wavelength of light from his experiments, the first measurements of the wavelength. No one ever did that before. In fact, his experiment gave us a relatively accurate measurements of the wavelength of light. So, giving an example, Young's experiment, Young was able to give the value of the average wavelength of sunlight. As about 570 nanometers. Right? We know today that it is about 555 nanometers. Well, that's really, really good. Not only, I mean, it'd be great if he was even just in the order of magnitude, which he is, but he actually almost nailed it. And this was the very first experiment to show you that there is a wave theory of light. And not only that, he was able to almost nail the average wavelength of sunlight on the head, 555 nanometers. So what is this experiment? So let me show you a picture that I drew up on PowerPoint. Okay, so get to my PowerPoint here. Share my screen. mean, I could try to draw this by hand, but I don't think I do as good of a job. All right, now, what you see in this picture is incident plane wave, electromagnetic waves or light coming to an interface. Now, this interface happens to be a screen. The screen has two holes punched into it. One S1, the other one S2. Now, Huygens wavelet or Huygens theory would tell you that that each of these points along these wave fronts, including these 2 points at these small holes, would be the source of their own wavelets, if you will. So you notice that there is a hole S1 and S2. Now this, again, we're looking down from the top, if you will. So we're really looking at slits from the top, and this is really a three-dimensional picture. These are screens. We're just looking at it from the edge on. We're looking at it from the, like we're looking from the ceiling on down, looking at this experiment from on high. Now we have two rays, if you will, that would go from we have one that would go from S1 to a point P. You know, again, we're seeing I'm labeled this as screen B for whatever reason. The one that has the holes punched on the left, the rightmost screen, I'm calling screen C. Now, if you were to look at the distance between these two holes, at the center, I drew a little line going from the midpoint of S1, S2, all the way across to O. O is a point along screen C that's basically a straight line from the midpoint of S1, S2. Now, if you draw we imagine a point P. The point P is at a height Y, a distance Y. I'm not saying a height, a distance Y from O over to P. Okay, so distance Y. Again, it's a distance. If you think about this, we're looking from on high. So it would be like going to the left, if you will, left of O. O would be, if you're looking at the slit straight to the wall, there's a screen on the far end of the lab. Well, P would be like on your left as you're sighting along the wave. It'd be on your left. Now, we imagine that there are rays S1P, which would be going from drawing a line from S1 over to P. We have another line we draw from S2 over to P. Okay, now, if I imagine the point O for a moment, let's just say I don't think about P for a moment. Well, the point O, I know that the waves at the holes are in phase. The waves at the holes are in phase. And if they reach the point O, they're still in phase at O. However, if I look at the point P, S2P has to travel a longer distance. It's longer than S1P. All right, again, if I draw the line S2P, it is longer than S1P. And in fact, if the difference between these two lines would be, if I draw a right triangle, if I draw a perpendicular from S1 down to intersect the line S2P, and I call that point B. That little extra distance, S2B, is the difference between whether these waves will be in phase or out of phase at P. If this extra distance, S2B, is an integral multiple of wavelengths, then you will have a maximum. You will have complete constructive interference, total constructive interference at P. If, on the other hand, that extra distance S2B is a half integral number of wavelengths, then the waves that will appear at P will be 180 degrees out of phase. And you'll have a dark place at P. You'll have you'll have destructive interference at P. The two waves will be 180 degrees out of phase, and at P you will see destructive interference. Again, the distance between these two holes is indicated as D. So again, let me remark one more time, and I'll go to the whiteboard. We're looking at this experiment from on high, from let's say from the ceiling. I have incident electromagnetic wave light coming from our left. If you look, as I'm looking down, I mean, it basically is incident, and it's going to hit screen B. You notice I have the screens labeled B and the one further down as C. Screen B will get struck by the incident ray first, the incident electromagnetic wave first, the light wave first. Now, there are two holes that are punched into screen B. One which I've labeled S1, and the other one I've labeled S2. Light will go through these holes. Now, when light is at these holes, they are in phase. Light is in phase. It's the same wavelength, right? If I were to imagine a point O straight down the center, if I imagine that there's a width D, as I call it, little d. Now the distance from screen B to screen C is capital D. Again, the distance, this is a macroscopic distance from screen B to screen C is capital D. Little d is the distance between the two holes. Now, if I look at point O, which would be a line I would draw from the midpoint between S1 and S2 all the way to the wall, the screen C, well, clearly the waves are going to constructively interfere there. They have gone, the waves from S1 and S2 will have both gone the exact same distance. I haven't drawn this on the diagram, but they would be going the exact same distance when they reach O. And so those two waves would indeed constructively interfere. But I'm looking at a point along the offset from O at a point P. We're going to say it's offset by an amount Y over at P. Now, I have waves coming from S2, or sorry, S1 on top, waves coming from S1 that are going to go to P, and I call that segment S1P. I have waves coming from S2 going to P. I call that line S2P. Now we can clearly see from this diagram that S2P is greater than S1P. So if I were to then, and again, I can also draw a line from the midpoint between the holes and where P is, and I can say that line forms an angle theta with respect to that line that I initially drew over to O. Now it turns out that I can draw a perpendicular from S1 down to S2P. Again, that's a 90-degree angle. And that angle, if you look at the geometry carefully, this angle at the vertex at S1 is also the same angle theta. The same angle that I said is the angle between the midpoint of S1, S2 over to P. This is the same angle theta. So the difference between the lengths of the waves from S1 to S2 is this line, this little length, S2B. If that distance is an integral number of wavelengths, you will experience constructive interference at P. If this distance is a half integral number of wavelengths, you will experience total destructive interference at P because the two waves will be 180 degrees out of phase. Okay, so let's talk mathematically what I just showed you. Let's go back to the whiteboard. And I'll try to reproduce this picture somewhat, but at least you know with my impoverished art skills, at least you'll know what I'm trying to draw. All right, so let's imagine here again, I have electromagnetic waves, plain electromagnetic waves coming. So again, it's plain light wave. Okay, it is approaching a screen. I call this initial screen B. Screen B, it's an opaque screen. It has two little holes. And these holes are separated by a distance d. Okay, this is my screen B. This is, I called S1. Try to do this well here. And this is S2. S standing for source. Now, if I go down, now let me before I draw this, try to draw my geometrical construction. Right? Give me patience, have patience with me here in my drawing. All right, let's try to do this. I just want to see how far away my ball has to be. I'm determining it based upon my drawing skills. All right. Here's my screen C. Further on down the laboratory. All right, and I'm calling this point P. And I can imagine, as I said, that my macroscopic distance from screen to screen is capital D. And I can imagine drawing a straight line down to O. And that is what I would call the central maximum. A central maximum would occur at O. Now, central maximum, what does that mean? That means a bright spot, the brightest of the bright spots. So a bright fringe. We're talking about slits, a bright fringe. Fringe being a line of light. You see stripes, basically. Occurs at O because the light from S1 and S2 travels the same distance. To get to O. Okay, so in order to get to O, that's what we have. Now, we're considering another point P. And I'm going to tell you that that point P is a distance y from this place O. Okay, now we want to say some things about P. We're going to say, well, clearly what we call S2P, which is this line going from S1 to S2, it's clearly going to be greater than S1P. All right. In fact, the difference between the two. Now skills are going to be challenged. I'm going to try to draw a line from that midpoint to P. And I'm going to say that this angle right here is theta. The angle that P makes with, if I not drew that line from O, which is really kind of the central axis of my whole problem, and I take an angle, I take a line, I draw it to P, that angle is theta. Now, if I were to draw a perpendicular right here, I have a right triangle, and I have letter B. I blow this up here. Let me blow this up. What do I have? I have distance D. Okay, remember the slit distance is D. This I'm calling S2. I'm calling this letter B. Okay, this is also angle theta. Okay, if S2B, so let's I need more room here. So remember this. That's our central maximum, right? So let me redraw this triangle a little bit here. I got this triangle that I'm going to redraw right here. Blow up. Okay, this is a distance d. Again, I'm saying that I'm drawing a line, a perpendicular down. This is part of S2P. Okay. Go again. S2B. This is angle theta, same angle theta. Now, what I'm saying here is if S2B, okay, again, not S2P, but S2B, that difference, that extra distance travel on the second ray, okay, if S2B is an integral number of wavelengths, then total constructive interference between the waves occurs. And I mean, basically the waves overlap. They're in phase. And a maximum, a bright spot, or a bright fringe, a maximum as it's called, occurs at P. All right. So that means that if this extra distance, S2B, is an integral number of wavelengths, that means that the two waves, the one coming from S1, the one that traveled the distance S1P, is totally in phase with the one that traveled S2P. And so you get a constructive interference. You get a bright fringe there. It's called a maximum. So what that means is that mathematically, if S2B equals m lambda, then there is a maximum at P. And m is a number. M is an integer. So m equals 0, 1, 2, ... M is called the order. All right. On the same token, if this S2B is such that the two waves are 180 degrees out of phase or a half wavelength out of phase, then you'll see nothing there. You'll see a dark fringe at P. So again, if S2B is a half integral number of wavelengths, then the wave from S, the wave from, moving along S1B or S2B will be 180 degrees out of phase with the wave along S1B. Okay, mathematically, what does this say? Well, essentially, mathematically, if S1B is equal to m plus 1/2 lambda, and that extra half a wavelength to give me the 180 degrees out of phase, then there is a minimum. This is a maximum, a minimum at P. That's a dark fringe. So again, this is bright. This is dark. And so you see these striped fringes. Central maximums is bright, dark, bright, dark, bright, dark. And you see these fringes, and they're most intense at the central maximum. And as they move away, they become more and more they become less intense, and eventually you don't see them anymore. All right, and so let's try to put this into more of a mathematical statement. So you're saying here that, okay, fine, I got this S1, S2B. That's the distance, that is the difference between one of these waves distance and the other wave distance. And we're saying, okay, well, if S2B is such that it's an integral number of wavelengths, if it's 1 times lambda, 2 times lambda, 3 times lambda, so on and so forth, it's an integral number of wavelengths, then I know that they will totally constructively interfere. They will completely line up. They'll be completely in phase. And there will be a bright fringe along at that location. If, on the other hand, if that same, I apologize, it's S2B, if that same S2B is a half an integral wavelength different, so that could be, M could be 0, could be 1/2, 3 halves, 5 halves, 7 halves, whatever. If it's something halves, not a whole number, then there will be a minimum. There will be 180 degrees out of phase. You'll have a minimum, a dark fringe at P. So you see these stripes. Can I put this in a more mathematical sense? Well, yeah, I can, because I know D and I know theta. And so I could say the following. Let's see, what is this? Opposite of our hypotenuse. I can say that the sine of theta, or I can say that the sine of theta is S2B divided by D. Or I can say that S2B is D sine theta. Yeah, I can say that. So what that means is that I can just take this S2B and put D sine theta here. I know the distance between, I'm given the distance between these two holes, and I can figure out many different ways. I can say, okay, well, I know the central maximum. I can measure that in the laboratory, and I can essentially measure Y. I can figure out simply Y and D, and I can get theta that way. I can get theta from the tangent. So I can certainly figure out theta. I can do that in the laboratory. I can figure out where the central maximum is. In fact, if we were to meet face to face and we're doing optics labs, we would actually study this. And we would actually go and see the central bright fringe on a screen, a little screen that we have in our lab kit, and we can actually go and figure out how far away is such and such bright fringe. We can measure that. So we can simply do, well, what is that? That's the tangent of theta, right? It's y divided by d. Well, I can get theta that way, and I can take the sine of it. So again, I can find theta just from macroscopic measurements in the laboratory. So that's easy. And of course, when I talked about this, well, here's S2b. Well, again, I can write d sine theta here as well. And this is what Thomas Young showed. So to simplify his, to put everything in a nice summary, I'm just going to try to do so. The two equations you get from the double slit experiment. So again, what is this? Well, we would say this is the double slit. This is the famous double slit experiment. Why? Two slits. What did Thomas Young show? That d sine theta equals m lambda, where m equals 0, 1, 2, ... That gives you the maximum. And d sine theta equals m plus 1/2 quantity times lambda. And again, m is a non-negative integer. 0, 1, 2, ... This gives you the minimum. And so you can locate the light and dark fringes of your interference pattern. So again, we use these equations to locate the light maxima and dark minima, fringes of an interference pattern. Basically a bunch of stripes. There it is. So d sine theta is m lambda, maxima. D sine theta is a quantity m plus 1/2 times lambda, minima. Again, you can use these equations out of the box. Again, there's nothing real. I'm not expecting you to derive these. These are, you can use these out of the box in solving Young's double slit experiment problems in the future. Let's work a few problems out. So OpenStax 27.6. Okay. OpenStax 27.6. At what angle is the first order maximum? For 450 nanometer wavelength blue light. Falling on double slits. separated by 0.0500 millimeters. Okay. That should be a question mark. All right, so the question is, at what angle is the first order maximum for 450 nanometer wavelength blue light falling on double slit separated by 0.500 millimeters? Okay, so what do we know here? Well, our lambda is 450 nanometers. First order maximum means m equals 1. And it meant that they start counting from, from the central. So first order would be 1, 2, and so on and so forth. And D is 0.0500 millimeters. So again, these are the things I'm reading off of this. Okay, so let's work the problem. I'll erase this for real estate here. So what I don't know is theta. I'll call it theta 1. It's the angle to the first order maximum. I'll just call it theta. M is 1. How do I know that? Because it's first order. Okay, first order. Remember, M is the order number. Lambda, the light that's coming in is blue light, 450 times 10 to the negative 9 meters. D is the distance between two holes. 0.0500, again, it's millimeters, that's times 10 to the negative 3 meters. Great. So maxima, right? I'm looking for the first order maximum. So the equation for maxima is d sine theta is m lambda. And I want theta. So what do? Well, I'm going to divide both sides by d. I have the sine of theta is m lambda divided by d. And of course, how do I get theta? I take the inverse, the arc sine or the inverse sine of both sides. I have theta is the inverse sine of m lambda over d. Okay, that's all there's to it. So now I got to plug in numbers. So theta is the inverse sine. M is 1, first order, times lambda, which is 450 nanometers, so 450 times 10 to the negative 9 meters. And D is 0.0500 times 10 to the negative 3 meters. And be very careful that you're doing apples and apples here, right? You want to have everything in terms of meters. Now, of course, inside the argument of the inverse sine or the arc sine should be unitless, right? You should have meters over meters. Remember, it was given you to your nanometers and millimeters, so you have to be careful. But when you do all this correctly, you'll find out that the angle to that first maximum is only 0.516 degrees. So these fringes are not separated by too much. So the first bright fringe, you have the central. So if you're looking at it in the laboratory, you have a central bright fringe, and then you'll have dark, and then bright again on either side. So I call this 0. We literally would have, the first, on either side. So there would be a distance, an angle that would go from, central max over to the left for the first order. And of course, it's symmetrical. You also have the same fringe pattern on the other side as well. We're just looking at one side of the fringe pattern. Okay, there you go. That's problem 6. And this is particularly for Huygens double slit experiments. And you're going to have other equations in this chapter that are going to look kind of a little bit like this one, like these equations, and sometimes that confuses students, right? Understand that what we're particularly talking about is the interference of light. Interference of light. When we talk about the diffraction later, the diffraction equation looks scarily similar to this one. Right? And it says something totally different. So I want to make sure that we're on board, that we're looking at interference, and we're looking particularly at a double slit experiment. Okay, OpenStax 27.8. That one says, what is the separation between two slits? For which 610 nanometer orange light has its first maximum at an angle of 30.0 degrees. Okay. Now, remember that in the first problem I had an angle 0.516 degrees when my slit separation was in terms of millimeters. We're going to find out here that in order for me to get wider angles, I need to have smaller slits. Okay, so that's one thing this problem is going to teach you. You'll see what we'll in a little bit refer to as a diffraction grating. Diffraction grating will be where we can actually machine slits to actually make them, have the lighter fringes be lighter, the darker fringes be darker, and the angles be wider. So we use those in biology, like looking at cancer biopsy and things like that. We oftentimes will use this concept of a diffraction grating. It's very important in looking at biological samples, for instance. So anyway, so what do we know here? We have two slits. Okay, what we don't know is D. We don't know D, but we know lambda. We're looking at orange light, 610 nanometers. Okay, first maximum means m equals 1. Remember, that's the order parameter, m equals 1. Angle theta is 30 degrees. So there's a number of different things we can tease out of this English here. So let's erase this for real estate purposes, and let's convert this into math. All right, so what we don't know is the slit separation. We don't know D. That's what we don't know. We know lambda. Lambda is the wavelength of the light. It's orange, 610 times 10 to the negative 9 meters. All right. Let's see, the order number. First maximum means m equals 1. And we're looking at the angle to that first maximum. That's theta equals 30.0 degrees. All right. So again, we use the Young's equation for maxima. Again, that's d sine theta equals m lambda. And we don't know d, we'll solve for d. Divide both sides by sine and theta. D is m lambda over sine of theta. Simple as that. M is 1. Lambda, 610. So 610 times 10 to the negative 9 meters divided by the sine of 30 degrees. We get that D is equal to 1.22 times 10 to the negative 6 meters, which is 1.22 micrometers or 1.22 microns. Again, for us to get an angle as large as 30 degrees, we have to pinch down that slit width down to micrometers. Remember in problem 1 or problem 6, the slit width was in terms of millimeters, so we can only get 0.516 degrees. So you want the light to flare out more, you have to pinch you have to make the the aperture smaller and smaller. All right, so look at OpenStax 27.10. That one says, calculate the wavelength of light. That has its third minimum. So we've been talking about maxima, and now we're going to talk about minima. Third minimum at an angle of 30.0 degrees. When falling on double slit separated by 3.00 micrometers. When falling on double slits. Separated by 3.00 micrometers. Okay, so here we go. Calculate the wavelength of light. That's its third minimum. Let's be careful about how we talk about the order associated there. Third minimum at an angle of 30.0 degrees when falling on double slit separated by 3.00 micrometers. Okay, so let's kind of just see. I think I have enough room to solve the problem here. So I don't know lambda. Now remember, one of the things that Thomas Young accomplished is this experiment. He was actually able to say, well, if you guys don't believe in wave theory of light, hey, look at this. I can actually give you the wavelength of light. Not only am I so confident that I have a wave theory, I can actually give you the wavelength. In fact, I can even give you the wavelength, the average wavelength of sunlight. So I think I actually have something here, right? For those of you who want to naysay. So again, Thomas Young was able to do this very calculation. He was able to give you lambda. Now, let's be careful here about the third minimum. What does that mean? Well, again, I'm looking at the minimum form. So let's see, minimum. That says d sine theta is m plus 1/2 times lambda. Well, let's see, the first minima is actually going to be 0, right? It's going to be 1/2 a wavelength up. So I got to start counting. I got to say 0, 1, 2. That means if it's a third minima, unlike maxima, minima starts counting at 0. That means that the minima, again, be careful of this on your exam. You need to be counting, you need to be at 2, not 3. Okay? Again, minimum. First one is 0, 1, 2. All right. Now, what else? I also know the angle to that third minima. Angle's 30 degrees. And I know one more thing. I know the slit separation, 3 micrometers. 3.00 times 10 to the negative 6 meters. All right. So I know all that stuff. What is it that I want? Oh, I want lambda. Let me solve this equation for lambda. Pretty easy. Lambda is d sine, oops, I did not give you the right equation here. There's an equal sign here. All right, d sine theta equals m plus 1/2 times lambda. Okay, so dividing both sides. Sorry about this. Minima. All right. Lambda equals d sine theta divided by m plus 1/2. All right, lambda is D, which is going to be 3.00 times 10 to the negative 6 meters times the sine of 30 degrees divided by, again, 2 plus 1/2, or 2.5. Well, I'm just going to be very explicit here. 2 plus 1/2. Remember, it's the third minimum. If I do it that way, I find out that lambda, I'll just write it over here. Lambda is going to equal 6.00 times 10 to the negative 7 meters, or about 600 nanometers. And 600 nanometers is about orange light. It's about orange. So it'll be orange colored, definitely in the visible spectrum. Even the previous problem said 610 was orange, so 600 should be orange as well. So again, third minimum should be an orange. The light that's coming, the light that I can actually tell you what the instant electromagnetic, what the wavelength of the instant light is going to be, and that's orange, based upon where are the maxima and the minima being spread out. I can tell you what the nature of the incoming light actually is. OpenStack's 27.13. That says, what is the highest order maximum? For 400 nanometer light, falling on double slits. Separated by 25.0 micrometers. Okay. What is the highest order maximum? We're looking for maxima. For 400 nanometer, that's our lambda, that's blue. Light falling on double slit separated by 25.0 micrometers, that's D. Okay, as you read that equation. Sorry, so let's remind ourselves, actually I could probably do it here. So maximum, what equation should I be talking about here? Well, Young's experiment, that equation is D sine theta is M lambda, as we derive. Okay, so what do I know? Well, I do know D, and that's 25 micrometers, or 25.0 times 10 to the negative 6 meters. I know D. I know lambda. Lambda's blue light. I'm using blue light. 400 times 10 to the negative 9 meters. That's my lambda. And I'm asking what the maximum is. Again, I'm looking for the maximum. I want to find the highest order maximum. Okay, so so in this problem, D and lambda are constants. And so let's just kind of solve for M, because I'm looking for order, right? I want order. So I have M equals D sine theta over lambda. All right. Well, M and lambda are constants. So the maximum M occurs for maximum sine theta. which is 1. So again, sine of theta, every time I put another angle theta in, that sine function gets bigger and bigger and bigger, right? Sine of 0 is 0. And so at some point, if I'm thinking about what am I doing? I have the original, I told you, that distance, that midpoint between the two holes and that central maximum O. Well, I'm just increasing the angle, The biggest maximum angle I can imagine having is 90 degrees, right? So if I make it 90 degrees, then I can find the maximum by just basically making sine theta equal to 1. So if I want M max, I just take sine of theta equal to 1. And I just get d over lambda. That gives me a measure of how many orders I can possibly expect. Because I max out that sine of theta. I max it out. This gives me an idea of how many possible orders I can expect. So what do I get when I do that here? Well, I find out that M max is going to be D 25.0 times 10 to the negative 6 meters. And I want to go apples and apples here, so I got to have meters over meters divided by 400 times 10 to the negative 9 meters. And I find out that, again, this is a unitless number because the meters cancel. I find out I get 62.5. Now, of course, M has to be an integer. 62.5 is not an integer. So that means for me, M max has got to be 62, right? Since M must be an integer. So I don't have enough for 63, but I do know that I have enough for 62. So I can possibly, I'll never see this many orders, of course. I might be lucky if I see maybe 4 or 5 or 6 orders, right, in experimental reality. But hypothetically, in theory, I could see as many as 62. I never will, but I could if I had absolutely perfect instrumentation. All right, so that's Young's double slit experiment. Now it turns out that we want to now we see two effects going on here. All right, with Young's experiment, we see one effect is that there is a flaring out of light through holes, through apertures. That's the diffraction. We see that when we have multiple holes, they interfere. We get the maximum minimum interference pattern. So what we like to try to do is we like to try to see if we can make this diffraction experiment this even better. Again, we're talking about 2 holes separated by, maybe we can get down to micrometers, but why don't we consider a situation where we try to make those slits as precise as possible. Remember, the smaller you make D, the greater the angles. So we devise what we actually call, as you'll see in science, you'll see this in biology many times as well. It's called a diffraction grating. All right, so that's what we're going to talk about next. It's called a diffraction grating. And it turns out that the mathematics behind this is almost exactly the same as, in fact, it is the same as what we just got done studying. It's just, a much more scientific way of doing this. So we have what is called a diffraction grating. Okay, and many people have seen this, even in non-physics classes, you've seen diffraction gratings. Essentially, a machine creates many parallel scratches on glass. and these scratches are micrometers apart. Very carefully machined scratches. The unscratched areas form the slits through which light passes. Light passes through these very narrow slits. Now I'm going to show you a little picture here, and then I'll try to reproduce it myself poorly. But I'm actually going to go to the textbook this time. Let's see if I moment here. I need to get to a particular picture that I want, and I lost that page. All right, let's go to the textbook. 1 second here, bear with me. And this is one of those chapters that I really heavily rely on pictures because my drawing skills are not so good. Okay, so here's a nice picture. Let me share my screen. Okay, so what you see is a diagram showing you a particular region of the diffraction grating. Now you'll see that there's all of these little holes are the space between the scratches that I'm telling you about. Light will pass through them. Now light gets bent the same way. All the rays of light get, I mean, you imagine they get, you know, if you're looking at a particular point or a particular screen a distance away, all these rays of light that'll be approaching that screen will all be parallel to each other. They'll all be different. They'll all have traveled a different length delta L. Now, if you look at this, the distance d between each of these holes is still d, right? We have the distance d between the holes. So if the angle between, let's say, you know, if you're to imagine the ray of light going straight through the slit, like you see here, you see this little dashed line. If the angle between where the ray is going, where the light is going, and that straight dashed line, that's angle theta. Well, if you do the mathematics, if that's angle theta, then the angle right next to it, if you see my mouse here, at the top vertex, those little triangle I'm pointing at, that would be 90 minus theta. Now, of course, this is a right triangle, so this angle right down here, this lower vertex, is theta. All right, so if we look at this, if the distance between one hole and one ray of light to the next is delta L, that delta L works out to again be d sine theta. So each of these rays of light lags behind the other, the previous one, its neighbor, by an amount d sine theta. Now, if d sine theta happens to be an integral number of wavelengths, then we have a very, very nice constructive interference. In fact, it is a very strong constructive interference. And so we have a situation where if d sine theta, if delta L, basically each of these light waves is delta L different from the previous light wave. Okay, so light wave number one, or light wave, number one is delta L or d sine theta behind light wave 2. light wave 2 goes d sine theta behind light wave 3, and all of these are, basically d sine theta apart. When d sine theta is equal to a maximum, they all will constructively interfere. You'll have a maximum. So, and it turns out, so essentially, let me draw this picture. Try in vain to draw this picture probably, but I'll do my best. So, what I just showed you in the diffraction grating, we'll kind of redraw what I just said, and I'll tell you again how this works. So, what we see is a piece of the grating, and so you have a scratch, a space, then another room for a scratch, a space. I'll draw a few of these here. Try to make these as uniform as I possibly can. So light comes through parallel, and it all gets bent the same way. Again, the distance between each one of these is d. Right? Now, they all get bent the same way. And so this one gets bent. Again, there's this dashed line I was telling you about. And so let's just say they get bent this way. This angle is theta. Okay. And then the next one remains parallel and it's bent. Next one remains parallel and it's bent. And so on and so forth, right? Now, what we want to consider the difference between one hole and the next. So again, we're going from hole to hole. What is this delta L? Again, this wavelength is delayed from the previous one by an amount delta L, right? What is that? Well, if we know this is angle theta, and I just showed you that this is also angle theta. Well, if I blow up this triangle, and here we go. This is a right triangle, there's a right angle here. This is D, this is theta, and this is delta L. Again, there's a triangle like this between each and every one of these little holes. So sine of theta is delta L over D. And so we see that delta L is D sine theta. Again, each of these waves is delta L different than the previous one. So each wave is out of phase or delta L behind its next neighbor. They're all out of phase, except, remember, delta L is D sine theta. However, if D sine theta is an integral number of wavelengths, then all waves constructively interfere. And we get a maximum. All right. Now, the nice thing about diffraction grating, so essentially, if you do this, then you essentially now have a condition for maximum, and it simply says that, again, you've already seen this formula: d sine theta equals m lambda, but now your m can take on the values 0, plus or minus 1, plus or minus 2, ... It can take on negative integers as well. Again, now what's nice, as I said earlier, is that this D is typically as small as I want to make it, which means that the angle will flare out more. So there's a lot of different, there's a lot of advantages to diffraction gratings. All right, so let me kind of erase this. Why do we use them? Why do we care about them? Well, there are a lot of advantages to diffraction grating. So because D, the slit spacing D is very small. Because the slit spacing D is very small, the angles are wider. That's one thing. I mean, you're not looking at little tiny narrow angles. You're looking at a much larger. The bright fringes are brighter. And the dark fringes are darker. Everything is much better defined. So if you want to try to understand interference patterns, diffraction grating is going to give you a much larger angle to deal with, instead of having little dinky angles like 0.516 degrees and trying to figure out something and measure anything with the little dinky angles. Instead, you have big angles like 30 degrees, much easier. The bright fringes are brighter. You want to see a bright fringe? Well, it's much, much brighter. The dark fringes are not just a little bit dark, they're very dark. So the darker fringes are darker. So again, everything is much easier to see, and it's much bigger. It's much easier to analyze when you're using diffraction gratings. So where are diffraction gratings used? So who uses them, and where are they actually used? Why do people care about it? And I tell you that if you're in the biosciences, you care about these. So the question is, where are they used, and why are they used? All right. So where are diffraction gratings used? Okay. So diffraction gratings are key components of monochromators. I can never say this word. Monochromators, I think they're called. I apologize if I'm getting this all messed up. Okay, monochromators used, for example, in optical imaging of particular wavelengths from biological or medical samples. Okay. Diffraction grating A diffraction grating can be chosen to specifically analyze a wavelength emitted by molecules of, say, disease cells in a biopsy. So diffraction grating can be chosen to specifically analyze a wavelength in diseased cells in a biopsy. Sample or to help excite strategic molecules. In the sample with selected frequency of light. So they're used to analyze disease cells, like you get in a biopsy. Okay, so diffraction gratings are key components of monochromators used, for example, in optical imaging of particular wavelengths of biological samples. Diffraction grating can be chosen to specifically analyze a wavelength in diseased cells in a biopsy sample, or to help excite strategic molecules in the sample with a selected frequency of light. Again, this is something that can be used. So again, we see these. There's a use for them in biology. So we also can use them in optical fiber usage. Again, this is biology. And we can go back to fiber optics. So in fiber optics, so another diffraction gratings can be used in fiber technologies. Can be used in fiber technologies. Okay, where fibers are designed to provide optimum performance. At specific wavelengths. Range of diffraction gratings are available for selecting specific wavelengths for such use. So again, you can essentially use them to essentially control performance of the fiber at specific wavelengths. Again, so we see that they're used in fiber optics technology. We see that diffraction gratings are also used in biology. I know they're used many places in biology. I mean, I'm just giving you one example, but again, diffraction gratings are no stranger to biology. They're used a lot. Okay, let's work some problems out here for regarding diffraction gratings. I mean, they're going to be very similar feel to the Young double slit problems. All right, OpenStax 27.21. That one says a diffraction grating has 2,000 lines per centimeter. Okay. At what angle will the first order maximum be? For 520 nanometer wavelength green light. Green light. All right. Okay, so a diffraction grating has 2,000 lines per centimeter. And I'll show you how to figure that out. That gives you D. At what angle will the first order maximum, again, M equals 1, we're talking about maxima, be for 520 nanometer, that's your lambda, wavelength green light. Okay, so to remember these numbers, I need the real estate here, so, okay. So first of all, we're told that a centimeter, 0.01 meters, has 2,000 lines. Okay. And the question I want to ask is, well, that tells me what the spacing is per line, which is D. So I work this out, that 0.01 meters per 2,000 lines, I work this out, I get 5.0 times 10 to the negative 6 meters per line. That is my D. That is the spacing between each scratch. All right. So given that this density, this line density, if you will, then I can write down, well, I know what D is. D is 5.0 times 10 to the negative 6 meters. Okay, and I can get D that way. Oftentimes you'll see what's called, they'll say that the diffraction grating is ruled by 2,000 lines per centimeter. Usually they'll say it's diffraction grating is ruled at 2,000 lines per centimeter. Though essentially, if you get a diffraction grating, you're going to be told this information. This is a manufacturing information. They know, the people who manufacture diffraction gratings know how precise they made their lines. All right, and so you can use that information to get D. We are allowing green light to fall on this diffraction grating. So we know that there's 520 times 10 to the negative 9 meters. We're told that. We're also told we want the first order. So again, we want the first order, maximum. Okay. So, and again, we want maxima. So maxima, D sine theta is M lambda. What is it that we want? We want the angle to the first maximum. That's what we want. We want theta. So we're going to solve for sine of theta. Sine of theta, again, is M lambda over D. And of course, you get theta by taking the arc sine or inverse sine of both sides. So theta theta is going to equal the inverse sine of m lambda over d, or the inverse sine. M is 1, lambda 520 times 10 to the negative 9 meters. And then we have d. D is 5.0 times 10 to the negative 6 meters. All right. And so we find out that the angle to the first maximum of the diffraction grating pattern is now 5.97 degrees. Now remember, the very first problem that we worked out was 0.516 degrees. So again, we're getting wider angles. It's a lot easier to see something that's like around 6 degrees than it is half a degree. Okay, let's look at OpenStax 27.23. Let's see. 23. All right, that one says, how many lines per centimeter are there? On a diffraction grating, that gives a first order maximum. For a 470 nanometer blue light. At an angle of 25.0 degrees. All right. So what do we know now? Well, we're being asked what that line density is. Again, what I'm going to need to do is solve for D. And then from there, I'll get the line density, right? So that's what I want. I really need to solve for D here. First order, m equals 1 maximum, okay. For 470 nanometer, that's lambda, 470 nanometers, blue light. Angle, okay, so that angle theta equals 25 degrees is the angle to the first order maximum. These are all things that I'm reading from this problem. So I need to solve for D. And then I need to get the line density. So remember these numbers. All right, so solve for D. So effectively I need D. Okay, don't know it. What do I know? Well, I know the angle to the first maximum is 25 degrees. I know that. I know the wavelength of the light that's striking the diffraction grating, 470 nanometers, blue light, or 470 times 10 negative 9 meters, blue light. And it's a first order maximum. That means that m equals 1, first order. First order. So I need to solve number 1 for D. So again, I want to use the maximum equation. So the maximum D sine theta is m lambda. I need to solve for D. Divide both sides by sine of theta. D is m lambda over sine theta. D So again, m is 1, first order. Lambda, 470 times 10 to the negative 9 meters, divided by the sine of what? 25 degrees. So I get that D is equal to 1.11 times 10 to the negative 6 meters. Okay, so that's my D, but I'm not yet done. What that tells me is that one line has a spacing of 1.11 times 10 to the negative 6 meters. I want to figure out how many lines there are per centimeter. So I want n lines, which I don't know, per, what's a centimeter? 0.01 meter. If I solve this for n, I get that n equals 9,000 lines per centimeter. Whoever's manufacturing this particular diffraction grating has made enough scratches so that there are 9,000 lines per centimeter. Okay. Let's look at OpenStax 27.28. That says, what is the maximum number of lines? Per centimeter. A diffraction grating can have. And produce a complete first order spectrum for visible light. This requires a little bit of thinking. All right. So here we go. So what is the, okay, so let's read this very carefully. What is the maximum number of lines? Okay, so I'm looking at some maximum now. Number of lines, D, which will become in capital N, per centimeter of diffraction grating can have to produce a complete first order spectrum for visible light. First order, that means m equals 1. That means that in the entire range of the spectrum, I need to be able to see everything from lambda min to lambda max. Okay, so let's kind of think about this. Let me erase this. I need a diffraction grating capable of anything that I can see in the, for the entire first order spectrum of visible light. That's what I'm saying. I'm looking, I'm manufacturing something that's capable of handling any part of the visible spectrum for at first order. All right, so again, I'm looking at the equation D sine theta equals m lambda. Okay, now I'm looking for m equals 1 versus first order. Now, that means that my equation simply quickly reduces to d sine theta equals lambda. Just right now, not to worry about m. M's just another thing to write down. It's first order anyway, so just get rid of it. It's 1. Now, visible light ranges, and this is an engineering problem. Visible light ranges from 380 nanometers for violet light to 760 nanometers for red light. And that's our design space. We need to select a D. Such that the entire range of such that for the entire range of theta, all wavelengths of visible light can be displayed. All wavelengths of visible light can be displayed. All right. Okay. Okay, so that's the engineering problem here. All right. I want the entire first order spectrum of visible light. Visible light ranges from 380 nanometers for violet light to 760 nanometers for red light. I want to be able to handle that entire range. You need to select the value of D. You need to select the spacing D in this diffraction grating such that for the entire range of theta, all the way from 0 up to 90, all the wavelengths of visible light can be displayed. That's the problem at hand. That's the engineering problem. Well, what we need to do then is if we know that, D, so we're going to select some sort of a D. Well, if we imagine a range of theta going from 0 to 9, so essentially we need to be able to handle the largest possible wavelength. If we can handle the largest possible wavelength, then we can handle the smaller wavelengths. So we need to design it for the largest possible wavelength. All right. So let's if we look at this a little bit more, if we kind of look at this equation a little bit more, we can say, well, what are we against here? Well, I want to solve some sort of again, I want to pick a D so that actually I want to be able to so essentially I want to think of D as being like lambda over sine of theta. Effectively, or actually let's do it this way. Let's look at it. Let's look at the way it's written. So lambda is D sine of theta, right? Let's look at it that way. So I like to have lambda max correspond to the maximum of sine of theta, which is 1. So worst case scenario, I can at least displace out lambda max in the first order spectrum as far, essentially, no matter what, all the other wavelengths will be handled because I can at least handle the maximum wavelength. So I can max out the value of theta, have that correspond to the maximum value of lambda that I need to be able to consider. All right. So that means that I really need to design. Again, violet comes for free. And so there's yellow and green and blue and all the other colors. I need to design based upon the maximum lambda, which would be red. If my system can handle red, it can handle everything that has a smaller wavelength than red. All right. So this corresponds to saying what I really want to do is say that lambda or lambda max is d times 1. Sine of theta is 1. All right. So my d needs to correspond to lambda max. So my lambda max really needs to be the same as d. My d, or I put it this way, my d must be lambda max, or my d must be 760 nanometers. Now, what does that correspond to spacing wise? Well, that means that one line would correspond to 760 times 10 to the negative 9 meters. That means that that corresponds to n lines per centimeter, 0.01 meters. If I solve for n, I find out that if I have n as 13,150 lines per centimeter. If I designed a diffraction grating with that, at least that amount, that number of that line density, then I will be able to actually display the entire first order visible spectrum. I need at least this many lines to do that. So if I'm gonna manufacture a diffraction grating that's going to be able to displace the entire first order visible spectrum, I need to have this kind of line density. Okay, let me look at another problem. OpenStax 27.29. That says the yellow light from a sodium vapor lamp seems to be a pure wavelength. But it produces two first order minima. I'm sorry, maximum. But it produces two first order maxima. At 36.098 degrees and 36.129 degrees. When projected on a 10,000 line per centimeter diffraction grating. Okay. What are the two wavelengths to an accuracy of 0.1 nanometer? Okay, so the yellow light from a sodium vapor lamp seems to be a pure wavelength, but it produces two first order maxima at 36.098 degrees and 36.129 degrees when projected on a 10,000 line per centimeter diffraction grating. What are the two wavelengths to an accuracy of 0.1 nanometer? So this is the famous doublet in sodium. So sodium, actually, the yellow light actually is actually composed of two very, very closely spaced yellow lines in sodium. So it's not pure wavelength, it's a combination of two wavelengths, two very, very close wavelengths. And so this is one of those famous line spectra characteristics of sodium. All right, and so let's and so you see this, for instance, in an experiment where you have two first order maxima, not one like you might expect if you think that sodium is pure wavelength, but one where you have some of it's from one wavelength and some of it's from the other wavelength, right? And so they're going to form two first order spectra, indicating that there are not just one wavelength corresponding to the yellow light you see, but two very closely associated yellow wavelengths. All right. Yeah, that's a very well-known result in quantum physics or spectroscopy. All right, so we have a couple of different thetas. We have 10,000 lines per centimeter, so that allows us to get us a D. Okay, and this just tells you how precise. We're going to want to kind of carry out our precision here very carefully, and first order. That means m equals 1. And all this information I can get out of this, out of reading this, right? So let's put this into math. All right, so what we want to do is find what these two lambdas are. All right, we have a couple of different lambdas. We don't know what they are. So we go back to our equation that locates maxima. Again, the equation that we want to look at is m lambda is d sine theta. Okay, now, first of all, I got to find d. So we're told that a centimeter has 10,000 lines. The question is, what does this correspond to? When I work this out, this tells me that d is going to be 1.0 times 10 to the negative 6 meters per line. Or basically the spacing is d equals 1.0 times 10 to the negative 6 meters. Again, I get that from the information of the line density of scratches on the diffraction grating. I'm looking for first order. So up here as well, I also know m equals 1, first order. And I know a couple of thetas. So what I'm looking for is lambda. Okay, so let me erase this. So I'm going to say, well, lambda 1 is d sine of theta 1. I have two different angles that I was given. Remember, m equals 1. So lambda 1 is going to be 1.0 times 10 to the negative 6 meters times, be very careful here. We want to do this trigonometry very carefully. Remember, our theta 1 was 36.093 degrees. And we have 3 decimal, but we're in the thousands of the decimals here. Theta 2 is 36.129 degrees. And these are very carefully measured angles. which means I can get very good values for the wavelength. I mean, provided that this is a good number, is 10,000. So again, sine of 36.093 degrees. So lambda 1 is going to be 5.891 times 10 to the negative 7 meters, or lambda 1 is 589.1 nanometers. That's one of them. Lambda 2, same math, d sine theta 2. That's 1.0 times 10 to the negative 6 meters. Sine of 36.129 degrees. Okay, I worked that out. Lambda 2 is 5.896 times 10 to the negative 7 meters, or lambda 2 is 589.6 nanometers. So again, these are famous numbers. The doublet in sodium, the two very close yellow lines in the sodium spectrum that give you the yellowish color of the sodium vapor is not pure wavelength, but a combination of these two wavelengths, 589.1 nanometers and 589.6 nanometers. Again, this is a famous result of spectroscopy. Let's do another problem here. OpenStax 27.34. We're going to do a little mathematical proof at this point. All right, OpenStax 27.34. Okay, that says, show that a diffraction grating cannot produce a second order maximum. For a given wavelength of light, unless the first order maximum is at an angle less than 30 degrees. All right. We're going to do a little proof. So show that a diffraction grating cannot produce a second order maximum for a given wavelength of light unless the first order maximum is at an angle less than 30 degrees. That means that theta 1 for first order has got to be less than or equal to 30 degrees if I am going to even see a second order. That's what I'm trying to prove. Okay, so how do we go about doing it? Yeah, this is a proof. All right, so to be guaranteed To be guaranteed to have a second order maximum, okay, we must be sure that this can be accomplished within a maximum angle of 90 degrees. All right. So in order to guarantee to have a second order maximum, we must be sure that this can be accomplished. Within a maximum angle of 90 degrees. You only have 90 degrees to deal with, right? So if you're going to have a second order maximum, it's got to be within 90 degrees. What does that mean? Well, again, let's go back to our original equation. We have m lambda is d sine theta. Again, that governs maximum. Okay, so what we're saying is that if I'm going to have a second order maximum, it means m equals 2. That means I better be able to write this. 2 times lambda has got to be less than or equal to d times the sine of 90 degrees. I need to be able to see the second order maximum within the range, within the maximum possible range of f theta. That means I need to be able to see the second order maximum within 90 degrees, between 0 and 90 degrees. It must exist someplace. Okay, that's what that means. What is the sine of 90 degrees? Well, that's 1. That means I need to be able to have that 2 lambda must be less than or equal to d, or lambda has got to be less than or equal to d over 2. All right. So right now, for me to even have a second order maximum, I need to be able to satisfy this relationship. I need to be able to max out my range of theta to be up to 90 degrees and be able to satisfy this worst case scenario. Okay. So that's got to be true. Now, that's the first part of this proof. So I need to be able to say that this is true. And I would write everything down in one sitting if I had enough whiteboard space. So anyway, what I know is that lambda must be less than or equal to d over 2. That's got to be true. Okay, now let's talk about first order. So first order maximum then says what? Well, now I go to first order. That says, okay, m is 1. Lambda, again, the same lambda, has got to equal what? It's going to equal d sine theta. It's going to be d sine of theta 1 max. Okay, now, and then I just told you here that, well, if I'm going to have any hope to have if I'm going to have a second order maximum, I better have that lambda is d over 2. I just derived that. So let's now substitute that in there. So that tells me that d over 2, 1 times lambda, I have d over 2, has now got to be equal to d sine of theta 1 max. My d's cancel. That means that the sine of theta 1 max is equal to 1/2. The sine of what is a half? Those of you taking the MCAT, you better have this memorized. Sine of 30 equals 1/2. That means that the maximum angle then I can have theta 1 max is 30 degrees, hence the proof. If I do not see a first order within 30 degrees, you can forget about having a second order. Second order will not exist. All right, so what I just proved to you is in order to be guaranteed, a second order maximum. The angle for the first order maximum must be less than or equal to 30 degrees. The angle for the first order maximum must be less than or equal to 30 degrees. Again, so that's one way of even caring to even look. If you find out your first order maximum is at an angle that is already over 30 degrees, don't even bother to look, because I've just proven to you here that it's not gonna happen.